Okay, cool. Let's see if the new setup works well. So what I'm trying to do is I think that what I should do is I should basically so I should basically just kind of try to decompose the whole Hamiltonian first, and then see what the hell the algorithm is for calculating the expectation value. Now I don't wanna. I don't wanna sample this stuff, so I don't wanna run this on the actual quantum computer here. So I don't wanna waste the. But I wanna get the. I wanna get the cubo, and so I'm gonna create the node. Can I just delete these cells? Cell. Can I delete the cell? How can I delete a cell? Insert, view, edit, delete cells. Q1 forecast and return. What is this? I think that makes no sense. To delete cells. Okay, cool. So now I'm here, and now I can create print a name node with the cubo, right? Print cubo. Okay, so this is the cubo, and I have the okay, cool. But the cubo is not the Hamiltonian, right? The cubo is definitely not the Hamiltonian, is it? Is the cubo matrix Hamiltonian, or is it? D-wave system. D-wave systems. Cubo Hamiltonian. Hamiltonian cubo conversion and vice versa. Oh, cool. So maybe there's a way to Hamiltonian cubo in Ising form is in the directly give you with the sample Ising, making give more information on the. Like how it's a picture of the paper. I've had good luck with converting Hamiltonians to Ising and cubo forms using PyCubo, where the Hamiltonian is in the form of the mathematical expression. The open source project is on GitHub. If Hamiltonian is in Ising format, it can be transformed into cube and vice versa. And vice versa. How can I be sure the Hamiltonian mentionable is as an Ising Hamiltonian? I don't know if you need to do that though. D-wave. Transform cubo into Ising Hamiltonian. Is that needed though? I'm not so sure. The Ising problem. It's a Hamilton cubo problem. Or cubo problems, binary or spin Ising. The expressions for an Ising or for a cubo problem do look very similar. In fact, Ising cubo. The Ising model. Okay, so the Ising model has basically the spins, right? And the cubo model is just true or false values. So there is probably a way to transform them. Okay, but let's just ignore this for a second. So I'm trying to see if I have the cue ball and I have a node, and now I want to go and let's just close all these. I want to go and say Google tensor network SVG or something like that. The singular value D decomposition. Mm. The crash course I've done is actually a really good one, by the way.
Yeah, so tensor.
Oh,
So
no.
what I'm trying to tell you today is about.
Oh no, I haven't watched this one actually. How can I find this tensor network docs, the documentation? These are this documentation, but the Nova video tutorials, basic API tutorial. Oh, here the reference documentation, basic API tutorial. So those you do constructions, splitting a node. Oh, here. Okay, so you have this will return two nodes and a tensor of the truncating error. The two nodes are the unitary matrices. If you want the singular values in its own node, you can use split node full SVD. Okay, so I can do these left edges, right edges. I don't know. So the left edges are the edges that will end up on the EU underscore S node, and right edges will end up on the VH underscore S node. And how do I know what the edges are? So quick start nodes edges. So if I just do these, so I have the node now, and I do something like that, but I need to define left edges and right edges. And this is the node that we start with. Left edges, right edges. So nodes, edges, node, rank dimension, copy node, node, abstract node, node collection. How do I know? Oh, matrix product states. So this actually has finite MPS, infinite MPS. So you start with a list of tensors, okay. But that's what I want to buy. That's what I want to build, right? So back in Union. So I mean, how to get MPS from a Hamiltonian? How to obtain? That's what's kind of this is extremely hard to find. Like stuff like that it's extremely hard to find. It's like if I print the cubo or node edges, does this exist? There two. Okay, there are two dangling edges. How is that possible? And the node, a named node. Nodes, node. Add edge, copy, disable, get all danglings. Okay, get all. Get edge, get rank, get tensor. How is it? Get underscore rank. So get underscore rank. Rank 2. Set name, syntax, get rank, get tensor. So I can just get tensor. Well, yeah, it's a two-dimension. Of course, it's a two-dimensional tensor. It's 2 dimensions. That's the point. Yeah. So that gets me the tensor. So I have 2 edges, right? Get edges. Get edge. Get all edges. Get all edges. Yeah. So can I just print like, I think I can also do like these, right? And that's an edge, yeah. So I could also, so I could try and do, you know, I don't know. This is these. I'm just really playing with these and I have no idea what I'm doing. I have absolutely no idea what I'm doing. So, and now basically I want to print, so I want to print get tensor. I want to see the tensors. Get tensor. This new keyboard I'm using is not the best. So I want to do these for V, for sorry, V edge and for S, and then the truncating error. I don't know what this is. What are we getting if we do this? Okay, so that should probably be an array or something. Can I just specify it like this? Yeah. No, what is this? Get tensor. But that is not a tensor. So this is just an error. Okay. Named edge. So those are the edges, and then this is the. So I guess I can say U V VH. Can I print like these in Python? Yeah, yes. So this is and this is sort of the diagonal elements. This is kind of the entanglement, isn't it? Okay. How can I... So now I have this matrix product state. And I can actually find out MPS. So if I now do a MPS TN finite MPS, and I give it like U, S, and VH as a list of elements. Yeah. Can I print an MPS? Finite MPS, canonize, check canonical, left. Check canonical, check orthonormality, get tensor at site. Got a node. So, do I just give it the parameters like this? We want a list. So that is a list, isn't it? What is it complaining about? Expect an MP array or a scalar. Got okay. So MP array. What have I done? Invalid syntax. What am I doing? What am I doing? NP array. Components node. Got class node. Type tensor. So you're getting tensors. No, you're getting nodes, and what you want is tensors. So maybe get tensor. That's what you want. Get tensor. Labels on tensor 0. What does this mean? Number of indexes doesn't match number of labels. So was it like, is this needed anymore? That's not anymore, probably. Yeah, that's the same problem. So what does this mean? Tensor TN Google. No, that's not it. It's going to be difficult to figure this out. Tensors, basically. So once the tensors. So what's wrong with these tensors? Get tensor, get tensor, get tensor. Okay, so what if I just give it, like, for example, this is still gonna complain. Okay, so that worked. If I give it like the VH, it works. If I give it the U, it works. Okay, so I guess it's the if I print the edges instead of the tensors, get all edges, and I do this for all of them. Maybe it's gotta do. U has a dangling edge. No, U has a dangling edge, VH has a dangling edge, and S has no dangling edges. So maybe this should be. I mean, maybe it just can't be S. But then what's the point? Maybe, okay, maybe I should not do it this way, but I should do it like, so, what was the repo? So basically, split node, US and VHS. So, okay, so this is the part where you're splitting something. So you don't get the S separated, but then you're pushing the S on both sides. I saw that in the video. So we'll just use it, we'll just call it split mode then. We'll just go with these. And so we're not gonna have S. We're gonna ignore the error because we're awesome. So we'll just do these, right? Not print these, not print these, and print the tensors. So this means now we split it in two things, right? Named edge. Get tensor. Too many values to unpack. What? Node left edges, right edges, split node. Oh, actually, I gotta take the whole thing, regardless. Cool. So, and then this is basically that's what we get. Okay, so this is it's what so I'll see if I can show the. Okay, so now we have the two tensors. Why a named edge? Whatever, we'll just print these. So I know it says unnamed edge though, but okay, and now U underscore S and VH underscore S. It still doesn't work. It doesn't like it. I don't know why it doesn't like it. Because now I have the two tensors. Get get all edges. Well, maybe because we actually have them connected. You know what I mean? Yeah, but I'm just getting the tensor, right? So I'm just getting the tensor. Oh, this is what's bringing the edge thing there. Why doesn't it like it? Number of indices does not match the number of labels on tensor 0. Does everything has to be labeled or something? Get edge, add axis names. Add axis names to a node, so I might have to do that. Maybe that's what it's complaining about. Because they're all dangling edge. Because it's complaining that it doesn't have the number of indices does not match the number of labels on tensor 0. So if I look for something like labels, there's nothing in here. Indices, nothing on here. And that is coming from contract tensors, whatever. Network structure. Number of labels on tensor. The length of the dimensions is different from the length of the network structure. Maybe I'll try to add the rank tensor axis set name, set tensor. Axis names. List of names for each of the tensor's axis. I don't know. How's it called? Add axis names. So I'll just say, well, score S. We'll just give it, whatever. I, and J, and we'll call it like these. What did I? Oh, sorry, I messed up with the press the wrong key. J, and then I'll do the same for VHS, and actually have VH in here. I really have no idea what I'm doing, so I'm just adding the labels, hoping that these will basically a name node, get access names, and add access names. Let's see, does this work? No. Maybe these have to match or something. You know what I mean? Like, and then it actually adds them. No. I have no idea. I have no idea. Finite MPS. Tensor network Google. finite MPS. Yeah, it's going to be impossible to find these. I don't think there's many people using this library and just putting stuff out there. Okay, but I get I could split those nodes farther, right? And so I could now kind of like split this farther into like 4 states or something like these, like a 4 nodes tensor network. But how do I turn it into an MPS? I don't know. Finite MPS. It just stored as a list as the central site also orthogonality center. The position of the central site is stored in these and it can be shifted using blah blah blah. Initialize from a list of tensors so by calling the class method random. By default is initialized in canonical form. The state is normalized and all tensors to the left of the center position are left orthogonal, and all tensors to the right of the center are right orthogonal. The tensor at the center position is neither left nor right orthogonal. The canonicalization can be computationally relatively costly and scales like these. A list of tensor objects. It's true. It's true the state. Okay, so maybe. Okay, so maybe I can put that to false. Because it seems like it's doing something. Oh yeah, there you go. Okay, so the canonicalize like false thingy. So what does this mean to canonicalize? Overlap in memorization, MPS1, and algorithms. I do probably want to read through some of those things. Overlaps in normalization. Oh. Or canonical forms. This is left canonical, right canonical, side canonical, bond canonical. Okay, so what are canonical MPS formats? I should probably really read the paper, the one that I was reading before. I'll have to look for it again. But it seems like I really have no idea what I'm doing. So I created the MPS, and what now? Like, what is these at all? Like, what's the algorithm for these? Like, what's the algorithm to find the or to approximate the eigen, so the ground state of an MPS state? MPS. Can I copy these? Why can I copy these? Copy. So MPS ground state. It's just not there. Let me take a look at Twitter, because I don't know if I bookmarked these. First stuff, these RRG algorithm of it all is a classic. What is the RRG algorithm? So, okay, so this is the paper that I want to read exactly. What is the RRG algorithm? The algorithm official? No. What? No, I want to see these. Reconstructed surface normals using RHE algorithm. What is these? Some 3D stuff. So, okay, so this is the paper that I want to take a look at. And if I just check quickly for ground state. So DMRG was originally proposed as a realization procedure over the ground state wave function of a 1D quantum lattice system. In the modern formulation, it is the variational optimization. Okay, in the modern, because that's what I thought. It's got to be somewhat like variational, because you got to kind of have to iterate over the network. So in the modern formulation, it is a variational optimization algorithm over the family of MPS. In particular, one sweeps back and forth over the different tensors of an MPS, with tensor coefficients treated as variational parameters in order to minimize the expectation value. Okay. There is something here. So in order to minimize, so you treat tensor coefficients as variational parameters in order to minimize the expectation value of a given Hamiltonian. At every step, the optimization can be written as a quadratic problem. Figure 1. So that's how you start, like A, or what is this? No. A is the matrix product state. So that's cool. So the idea is those are different decompositions you can build, I guess, of a Hamiltonian or a matrix, like of a tensor in a tensor network, that maybe then allow for certain algorithms. Okay, that's quite cool. So, quadratic problem for the tensor parameters, which can be solved via standard linear algebra. The method also makes use of other tricks, such as the canonical form for open boundary conditions, in order to improve stability and performance. Okay, so there's some canonical form for open boundary conditions. It can also be adapted to translationally invariant systems in the thermodynamic limit, the so-called infinite DMRG, blah, blah, blah. There's also extension of the method to deal with periodic boundary conditions as well as low energy excitations for open boundary conditions. Okay, and then we move to something else. Time evolving block decimation. This method allows to compute the time evolution of an MPS. Okay, now we're interested in the we're interested in the density matrix renormalization group. This is what we want to do. Okay, so this is, I was just confused all the time. That's what we need, the DMRG algorithm. This is explained in the paper as well. Some history. DMG. So, algorithm. As a numerical algorithm for the efficient truncation of the Hilbert space of low dimensionality strongly correlated quantum systems based on rather general decimation prescription. So there's some interesting paper. That's what, okay, so at least I know, at least I figure out what we, statement of the problem. Okay, so we'll go through these steps of the DMRG algorithm setup. Before beginning DMRG, it is imperative to bring the initial MPS into an orthogonal form via Gaussian summation. Here we will choose to begin the DMRG algorithm assuming without loss of generality that the MPS tensors 2, 3, and n are all right orthogonal. Okay, so we need to get them right orthogonal. Cool, we have something. That's what we, I guess, have. And then at the end, what do we get at the end? Adaptive restoration of MPS form. That's pretty nuts. After the bond is optimized, the MPS form here, unless equation 1 has multiplied the singular values into the right form tensor. Turn. So is it what we really... The density matrix normalization group is an adaptive algorithm for optimizing a matrix product state such that after optimization, the MPS is approximately the dominant eigenvector of a large matrix H. Okay, so what you get at the end is you get an eigenvector. The dominant eigenvector, I guess that means the lowest energy one. I don't know. The matrix H is usually assumed to be a Hermitian matrix, but the algorithm can also be formulated for more general matrices. Okay, so I gotta bookmark these somehow. Can I bookmark these? Bookmark. Cool. Yeah, perfect. We'll leave it here. Awesome. At least I feel like I moved one step forward, you know.